Next, we are going to use another descriptor for the motion, and it's velocity. But since this is rotational motion, we are using angular velocity. Okay, so that rotation brings the another word, which is angular. But again, you can still use what you know about velocity, how it was related to position, and we're going to do the same thing, but instead of using x, y, z for position as we use theta for velocity, instead of using v, we are going to use omega. Okay. And so what is velocity? It tells how fast the object is rotating, because this is the angular velocity, not just velocity. Like we did for a translational motion, we can define both average and instantaneous angular velocity. So how do we find our average velocity? It was over a finite time, right? No, I was trying to draw a star. Okay. So it was over a finite time, and you know that it's the change in position over time. So delta theta over delta t. And I'm just gonna write the linear version here. We had v vector bar shows the average, and we said delta x. So if this was the for the x, and that's delta x over delta t. Or if you use the general equation, so I think that would be even better. Instead of writing the x component, I'm gonna get to the, let's see. So let's just get rid of that, and then let's use the general equation. You can also see those from the equation sheet, and that would be delta r, three-dimensional position vector, right? So you're replacing v with omega, and r with theta in this case, because these are angular stuff, okay? But everything else is the same. And delta means final minus initial, so we're doing theta 2 minus theta 1 divided by t2 minus t1. 2 is for the final case, 1 is for the initial case, okay? And what is instantaneous angular velocity? It is for an infinitesimally small time, right? So we are going to make that delta t go to 0, and we're going to take the limit. And when you take the limit, this definition here is the definition for the derivation, and that is d theta over dt. Just like in the linear motion, this would be dr over dt, right? Again, that dr could be x, y, or z, or combinations of those, so I'm just writing it in three-dimensional case. And in the angular stuff, we are a little bit sloppy in the vector treatment, so the notation wise, so when I write it in the you can see that when I write it in linear form, I make sure that each side has vectors, but it looks like there's no vector sign here. The position is a vector, actually angular position is a vector, but we are not putting an arrow on top, okay? But you already know that these are vectors. Okay, so the notes, units for the angular velocity is, again, look at the equation, theta over time. Theta is radians divided by seconds, right? So this is the SI unit. But radians could be given in revolution, or and the time can be in terms of minutes. And RPM, revolutions per minute, is also commonly used, and you will see that in the problems. And that means we need to convert RPM to radians per seconds. How do you do that? You convert revolution to radians, and then minutes to seconds, and then you're gonna get the radians per second that way. And again, for the average, we put the bar. For the instantaneous, there's no bar because bar means it's an average, right? So omega is a vector because it's the velocity. Okay, just like the linear velocity is a vector, v, omega is a vector as well. And it points along the axis of rotation. And the direction is given by the right-hand rule. Sometimes you'll see this as RHR. Then you know that this means right-hand rule. There's also left-hand rule, which is LHR. But I'm never going to talk about that. So it's always right-hand rule that we use. And so what this is then, So it says that the omega, the angular velocity, points along the axis of rotation. Okay, that axis, so look at the axis of rotation and try to orient your thumb along that direction. Okay, so it's just like I'm gonna do my show you my drawing skills here. That is my thumb. Okay, and look at the rotation, axis of rotation. I'm gonna curl my four fingers, okay, along that direction. So the four fingers are stick together, they're parallel to each other, but thumb is stretched out. And what I'm doing is I'm following my following the rotation direction, that arrow here, and with my four fingers. Okay, but realize that the disc is kind of given in a perspective. So when you follow that, the thumb is gonna be along the axis of rotation, which is perpendicular to the disk, the rotating object. Okay, so try to see the perspective given in the problem as well. That gives even more challenges in terms of right hand rule. And on the other side, so if you're kind of looking from if you look at another, like the opposite direction of rotation, then you are going to switch your thumb downward and your four fingers are rotating the other way around. And this the first rotation is counterclockwise, right? So we're going to use CCW, and this one is clockwise. If you're looking from the top, that's the direction that you see. So if it is counterclockwise, your omega is coming out of the disk. If the disk is rotating clockwise, then omega is into the disk, right? And that's how we're going to use right hand rule. There's a lot more coming up with the right hand rule, and it's very important. But right now, what I want you to relate is counterclockwise is coming out, right, from the page. And if the page is rotating kind of counterclockwise direction, that also means the same thing as coming out. And going in is related to clockwise. Okay, and you don't need to memorize this, you just need to use your right hand. And make sure to use right hand because this is specifically not a left hand rule. So I've seen so many people using their right hand to write things, and then the other free hand is usually the left one, so they're trying to do the right hand rule with the left hand. That doesn't work. There's a reason that it's called right hand rule. Okay, you have to stick with your right hand on this. Again, we will discuss a lot more on this coming soon. And we will typically take omega to be positive for counterclockwise rotation. That's kind of the convention. And the reason for this is, so if you draw the Cartesian coordinate system, I'm just going to do it here. So let's say this is my x, y. So z would be this direction, right? This is the perspective view, but what I'm going to do is I'm going to now look at the plane only, x and y. And in this case, z is coming out of the page, okay? Z is out of page. And that's the positive z. Okay, these are only the positive axes. And you know that in Cartesian coordinate system, all these, it's called that because they're all perpendicular to each other, right? So let's try to understand. If I go from x to y, okay, when I go to x to y, so that's kind of the rotation direction. Follow that direction with your four fingers. Make sure your thumb is stretched out. When you do that, this direction is what? Counterclockwise. And what is the direction of the thumb in this case? Do you find out, and do it here too, counterclockwise? When you do that, do you see that your thumb is coming out? So you're really seeing a dot. Kind of, if you look at the top view, you're seeing the tip of the thumb, right? And that is the z direction in this perspective, right? That is the thumb, and that's the z direction, and it's positive z direction. The perspective view, yeah, it looks like it's lying on the z direction, but from the if you put the axes x and y on this plane, you're just seeing the tip of the thumb, and this, what I've just did, like the circle, there's a dot and circled, that is out of page representation. Okay, so we're gonna say, if you see this, you will see out of page. And then we'll say that if you see a cross, that is into the page. Okay, these are going to be important details. I never, again, memorize this. There's an easy way to kind of think about this. Think about a screw, okay? And I was able to do a nice circle. The things we learn with this online learning, right? I'm gonna try to make this. Okay, so like this is just a screw. Okay, I'm not gonna worry about too much details. But if you look at the top, what do you see? That you see the cross, right? So if you're looking from this way, then you're seeing that the top. So this is what you see, because the screw is into the page or into the wall or into the surface. So if this is what you're seeing, that's into the page. But if you're looking from this side, what do you see? You see the tip. If you're seeing the tip of the screw, that means it is coming out, right? So that's like how it is. How these symbols were chosen, because the tip shows you that it's coming out, and the cross shows that it's in to the page or board or whatever it is, surface. And these two representations are going to be very important. Okay. Again, we will talk more about it, but I want to introduce it here. And next thing, we are going to discuss angular acceleration, and I'll do that in the next video.